wave function. Before going to that one, what is the wave actually? What is the wave? Already you know this definition. What is the wave means?
It is the motion and direction of the particle.
Yeah, okay, that is also correct. And it is very generally disturbance in the medium, or you can very in childhood we used to study this one, disturbance in a medium or propagation of disturbance in a medium. Okay, that is the general wave definition. Okay, suppose if you throw one stone in a water, you will see the some waves. Okay, here also wave means same, but generally we know if you take light waves, if you take light waves, okay, these waves are like electromagnetic waves, like electric field is there, magnetic field is there. If you take sound waves, okay, if you take sound waves, this is also, it will have some pressure variations. Okay, some this much pressure variation. Okay, like that. But what matter waves are having? Okay, matter waves, we don't know what is the wave equation for matter waves. Okay, so Born, what he did, he predicted some wave function for this matter waves. Okay, but up to now de Broglie proposed electrons or material particles behaves as a waves, that is matter waves he called. Okay, or every microparticle, moving microparticle is associated with a wave. These waves we are calling de Broglie waves or matter waves, but we don't know wave function of that one. Generally wave function or wave function is generally, what is the wave function means, what this will do means, it will predict or it will gives the information about nature or behavior of particle, nature or behavior of a particle. Okay, behavior of a particle. Okay, so or you can say nature or behavior or motion or state of the particle, or you can say state of the particle. The wave function definition is, it gives the information about state of the particle, or you can say nature or behavior or motion. Okay, whatever you can write. Okay, this gives the information of particle. Okay, how it is moving, what is the amplitude, what is the frequency, what is the intensity, this type of information this will give. Okay, this is a general wave function. Okay, suppose we don't know the wave function for matter waves. Okay, if you see light waves, we have a some electric field. Electric field is called some equation, and magnetic field is called some equation. Or sound waves also there is a similar equation. But here we don't know what is the wave equations here. What is the wave equation we don't know. Okay, suppose if a particle is moving like this, suppose in parabolic nature particle, if you throw some particle, it is moving a like a parabolic. Okay, what is the equation? Y square is called 4ax. This is one wave equation for a particle. Okay, or if you see in classical mechanics, if you throw any particle or if you drop any particle like this, here you have a building. Okay, from the building you have thrown a one particle, one mass or one stone. You have some expression for this, right? You have some expression this particle, but we don't know what is the expression for this matter waves. Okay, for that they are trying to derive the expression for these matter waves. Okay, generally first what they have done, the Max Born, what he just interpreted, not derived the expression, he interpreted some wave function. Okay, after that, after bonds, this Schrodinger came and he derived the expression for wave equation of matter waves. Okay, now we will see generally wave function is associated with wave function. Just I am writing shortcut. Okay, wave function is just a, it is associated with position and time. Position and time. Okay, so generally we cannot if it is a classically we can say some particle is here, some bus is here. Suppose bus is going at some time, we bus is here at Tarnaka station. After some time the bus is at Sikindrabad. So just we can say the, we cannot directly say the wave function of RAF. Please mute. You cannot directly say where the particular this thing is located. Okay, we cannot say directly using only position. We cannot say. Suppose if you so it always there should be a time. So instant of time. Suppose at the time 9 o'clock bus is at Tarnaka. At 9:30 bus is at, we are saying 9:30 at Sikindrabad. So we are mentioning time. Otherwise we cannot say, we don't know which location the bus is there, or which location that particle is stayed or stored. We don't know. Without time, we cannot predict the position of any particle. Okay, that's why we are always wave function is generally position as a function of position and time. Position and time. So here the wave function is what we call, just mentioned a wave function psi. Okay, psi is the wave function. Okay, and also this is wave function. It is a function of position and time. Okay, position and time. So we have considered here only one dimension, but this is not right. So you have to always mention, always write x, y, z. Three coordinates are there as a function of psi. Is wave function is always position and time, position and time. Okay, and suppose this is the wave function predict the state of the particle in a atom, state of the particle or state of the electron in a atom. Okay, they use it to explain the how the electron behaves as a wave and how it will change with a function of time and position. They used some expression, that is wave function is psi. Okay, psi is used to just as simple as the wave function is used to explain the state of the particle. Okay, used to explain the state of the particle. That is here in a microparticle, or you can some microparticle, electron or something like that. Okay, so this psi also, if you see this psi is, we cannot measure, right? It is a completely mathematical expression. Okay, this is mathematical. We cannot observe or we cannot measure this one. This is not observable quantity, not observable. Okay, so this psi is always a general mathematical expression. We cannot measure, just we can derive the expression, we can solve the expression, but we cannot measure, we cannot observe the wave function. Okay, and also if it is psi is the complex conjugate function also. If it is psi is a plus ib, what is the psi star? You can write psi star, complex conjugate of this wave function, a minus ib, right? What is the conjugate here? Minus, right? This is the, it is also some complex conjugate function. Okay, mathematical function, and it will not observable. And also always you have to write wave function as a function of position and time, position and time. Okay, and also here always this also always a, it does directly doesn't have any physical significance. It doesn't have any physical significance because it is not observable, right? Physical significance. Okay, no significance. Okay, only psi doesn't have any significance because it is not observable. Okay, it will, so that's why we are taking probability density function. What is that? Probability. Okay, probability density function. We'll see what is this probability density function. Okay, probability density function means psi star psi. Psi star psi we are calling a probability density function. So you cannot this simply wave function doesn't have any significance. That size doesn't have any physical significance because we cannot observe. Just we cannot see that wave function. Only we can derive the expression. We can solve the expression. Okay, for that, but we don't observe this wave function. But how you will predict the nature of particle? How you will predict the nature of particle? Okay, that's why we are taking probability of finding a particle. Probability of finding a particle. Okay, generally see, if you toss a coin, if you have a coin here, okay, some coin here, you toss it. Okay, whether it will we cannot say exactly it will get the tail at the, exactly we cannot say it will get the head, right? Isn't it? Can we say exactly whether we will get head or whether we will get that tail? We
No,
cannot say,
no, sir.
right? So that's why we are always using probability of getting the head, probability of getting the tail. Here also in quantum mechanics, we cannot find the exact position of electron. Okay, suppose here a nucleus is there, electron is revolving around the nucleus. Okay, at time t1, electron is here. Time t2, electron is here. Okay, the position is changing accordingly with time. Okay, as a function of time. Okay, we cannot exactly predict the where this electron is located. That's why we are using probability of finding the electron. Okay, probability. Maybe it is here at time, instant of time t here, or other after some time maybe it is here. But we don't know exactly location of electron or any microparticle. That's why we are using a probability of a probability density function, that gives the probability of finding the microparticle or electron, you can say, or material particle, whatever you can say. Okay, that is probability. That's why we are using always term here probability density function. Suppose if it is wave function psi is, if you can able to observe this one, we can measure it, but this is not observable quantity, we cannot see the wave function directly. So we can have expression but you cannot see. That's why we cannot directly locate the electron. Okay, that's why we are using probability function to identify where this electron is located, where this electron is, which place it is located. Okay, that's why we are using probability density function. Suppose uh, you can say at the sometime it is here, after some time here, that is probability only. Probability means what? Probability means what is mean by
To
Having a
guess, sir.
probability?
chance.
Huh?
To guess.
Possibility of that.
Yeah, it is a just chance of finding, or chance, just chance only. Okay, not the exactly. Okay, that is the probability. Okay, so that's why we are using probability density function. It is having some significance. Okay, that's why we are writing probability p is equal psi star psi, and psi star is the complex conjugate of this psi. Okay, or if you take limits, okay, if you take limits, you write minus infinity to infinity, infinity to infinity. Always this is volume, you have to write dx and dy and dz. Okay, dx dy dz at a time t, at time t, or you can write always at time t, some t value. Okay, this p is the probability of finding the electron at time t. So here we have a, maybe we have 80% of finding the particle at this position. We have 80% of finding the particle, but another place we have 20%, another place 30%. That depends on location and time of the particle. Okay, that is the use of this particle. Okay, use of the this probability density function. Suppose if you want to write this probability density function in two dimensional, just if it is three dimensional, you have to write here integration also three times, because you have to integrate with respect to z, with respect to y, with respect to x. Suppose if you want to xy plane, that is only two dimensional. Okay, if you want to two dimensional, you write psi star psi dx and dy. This is xy plane. Okay, suppose you want to write one dimension, you just write only one integration. This is infinity psi star psi only dx. Okay, so here if you want to integrate in xyz term, corresponding to xyz, it will be complicated. That's why we are first we will derive in one dimension, after that we will implicate in three dimensions. For simplification only, we are reducing the dimension. Okay, this is the probability density function, and this is the interpretation of wave function. Okay, this is the few about the wave function. And so what is the maximum probability? What will get the maximum probability? What will we have maximum? How much we will be? The always this probability is, what is the maximum probability of getting head in a kind? Just if you
1 by
toss
2.
0.5.
0.5 uh, maximum total. What is the total probability?
1.
Yeah, here
1 by
also
2.
if it is getting the head 1 by 2, our total probability maximum total probability is always only 1. Okay, it is equal to 1 only. Psi star psi. Okay, psi star psi dv I am writing, just this is equal to always 1. Okay, this is always equal to 1. This is we are saying normalization condition, or you can say normalization. Okay, you can say normalization. Okay, these are the few Bonds interpreted few things. Okay, psi is not a, it is doesn't have any physical significance because we cannot observe the wave function, and it is wave function is always position and time. Okay. Okay, just he interpreted, but he did not derive the expression for wave function. Okay, after that he proposed probability density function. Using this probability density function, we can estimate where the we can find the particle, which location or which time or on what time we can find the particle, or we can predict, we can, he just predicted means that is probability. Okay, just finding the probability density means finding the probability of finding a particle, just as simple as. Okay, that is the probability density function. It is maximum is equal to 1. Okay, now we'll go to the next as Schrodinger in time independent equation. Okay, time independent and time dependent